Welcome to our exploration of recurrent neural networks. This lecture will guide you through understanding these powerful neural networks, which are specifically designed to process sequential data like time series, text, and speech. Unlike traditional feed-forward networks, RNN possess an internal memory, allowing them to consider previous inputs when processing current information. The core of a recurrent neural network lies in its recurrent layer. Imagine a loop that enables information to persist from one step to the next. At each moment in time, say t, this layer takes the current input, xt, and the hidden state from the previous time step, ht-1, to generate a new current hidden state, ht, and an output, yt. Mathematically, this process involves weight matrices and bias vectors combined with activation functions to transform the input and previous state into the current state and output. In practical terms, using a library like Keras, a simple recurrent layer can be easily implemented. Let's look at an example. We'll import TensorFlow, sequential for building our model layer by layer, simple RNN for our recurrent layer, and dense for a standard output layer. We then define a simple sequential model. It starts with a simple RNN layer, which has 32 units and expects an input with a flexible number of time steps and 10 features. Following this, a dense layer outputs a single value. When we summarize this model, we can see its architecture, including the number of parameters it will learn. While simple RNN provide a foundational understanding, they often struggle with a challenge known as the vanishing gradient problem. This issue makes it difficult for them to learn and remember long-term dependencies within sequences. To overcome this, more sophisticated recurrent units were developed, most notably long short-term memory, or LSTM, and gated recurrent unit, or GRU networks. Long short-term memory networks, or LSTM, introduce a clever mechanism called gates. These gates act like intelligent switches, controlling the flow of information through the network. This allows LSTM to selectively remember or forget information, making them highly effective for sequences with dependencies that span many time steps. An LSTM unit typically features three main gates: the forget gate, which decides what information to discard from the cell state, the input gate, which determines what new information to store, and the output gate, which controls the final output based on the updated cell state. These gates use sigmoid and tanh activation functions to regulate the information flow through a series of weighted sums and element-wise multiplications, ultimately updating the cell state and hidden state. Gated recurrent units, or GRU, offer a slightly simpler yet equally effective alternative to LSTM. They streamline the gating mechanism using only two gates, an update gate and a reset gate. The update gate decides how much of the past information to carry forward, while the reset gate determines how much of the past information to disregard. Despite their reduced complexity, GRU often perform similarly to LSTM on many tasks and are generally less computationally expensive. Now, let's see a concrete example of an LSM in action using Keras. We'll use a dataset from scikit-learn, the California housing dataset. Although this isn't strictly time series data, we can structure it in a way that allows us to demonstrate an LSTM's capability. First, we import necessary libraries, fetch California housing to load our dataset, train test split for data partitioning, min-max scaler for feature scaling, and num.py for numerical operations. We load the housing data, separating features X from target Y. We then scale the features to a range between 0 and 1, which is common practice for neural networks. Crucially, we reshape our data to fit the LSTM input expectation: samples followed by time steps and then features. For this demonstration, each sample will be treated as a sequence of length 1 containing its 8 features. Finally, we split our data into training and testing sets and print their shapes to confirm the restructuring. Our training data now consists of over 16,000 samples, each with one time step and 8 features. With our data prepared, we can build our LSTM model. We again use Keras sequential model. This time, we add an LSTM layer with 50 units using a ReLU activation function and specifying the input shape based on our training data, one time step and 8 features. This is followed by a dense layer with a single output unit, as we are predicting a single housing price. We compile the model using the atom optimizer and mean squared error as our loss function, which is suitable for regression tasks. A model summary again shows us the layers and the trainable parameters. Next, we train our model. We use the fit method, providing our training features and labels. We train for 10 epochs, setting aside 10% of the training data for validation, and keeping the verbosity level at 1 to see the training progress. As the training runs, we can observe the loss decreasing for both the training and validation sets over the 10 epochs, indicating that the model is learning from the data. After training, it's essential to evaluate our model's performance on unseen data. We use the evaluate method with our x-test and y-test sets. The output shows us the final test loss, which provides a measure of how well our model generalizes to new data. In this case, our test loss is approximately 0.54. This example effectively demonstrates how to construct and train a straightforward LSTM model using Keras, leveraging a scikit-learn dataset. The model was trained to predict housing prices by treating the given features as a sequence, showcasing the LSTM ability to handle such structured data. In conclusion, this notebook has provided a comprehensive overview of recurrent neural networks, emphasizing their unique capability to process sequential data. We move beyond simple RNN to delve into the more advanced architectures of long short-term memory and gated recurrent unit networks, highlighting how they address the limitations of their predecessors in managing long-term dependencies. Finally, we brought these concepts to life with a practical demonstration of building and training an LSTM model using Keras on a real-world data set. Understanding these recurrent architectures is fundamental for tackling a wide array of sequence-based tasks across various fields, including natural language processing, time series analysis, and speech recognition,